very quickly, to wrap things up, HMM topologies, there are different ways of structuring your hidden Markov models. When you have in your initial transition matrix, if you have a 0, that 0 indicates that there's no connection between state I and j. But if you're running EM and you started out with a 0 in a particular state, you will never change that 0. That transition will always be 0. And this allows you to basically break connections up front. Before you run EM, you've already said that this connection will never exist. And that allows you to impose some structure on your hidden Markov model. Okay? And we call that hidden Markov model topologies, different ways of structuring the hidden Markov model, and that will depend on your problem that you're looking at. So almost all of the examples that we looked at, we had a fully connected hidden Markov model, which means that every one of my states are connected to all the other states and itself. Okay? And you can have transitions between any state in your hidden Markov model. I also showed you the example for speech recognition. And speech recognition very often uses a left to right topology for your hidden Markov model, because speech is actually a causal thing, right? Where what happens in the future only depends on the past and not so much on. That's not entirely true, actually. So in your brain, you actually do a little bit of planning as well. So when you're generating speech, there's a little bit of a look at it. But in many speech recognition and speech synthesis examples and applications, you use a left to right topology. So you can't go, if you're in this state, you can't go back to that state. There are many, many more things to say about hidden Markov models. For transitions that never happens in your data, or for outputs that never happen in your data, you also need to regularize for those cases. So unseen events, like we did with n-gram language models, you need to regularize for those cases or smooth. So many of the n-gram language modeling smoothing techniques that we looked at can also be applied to hidden Markov models. Okay? Add one smoothing, right? You can add one to all of the transitions between a verb and a noun, even if that, for some reason, never occurred in your data set. There are also extensions of hidden Markov models. So all the hidden Markov models we looked at was first-order hidden Markov models, which means that when I enter a specific state, it only depends on the single state that preceded it. That's a first-order hidden Markov model. You can have second-order hidden Markov models where basically when I'm transitioning into a state, it looks back 2 steps into the past in order to figure out what is the probability of entering the current state. Johan de Pre did his PhD on higher order H&Ms. He's probably a world expert on that. The very last thing to say about hidden Markov models, I use this example of part of speech tagging. It's actually quite rare to use hidden Markov models, either supervised, where you have a labeled state sequence, or unsupervised, where you don't have the parts of speech tags and you need to infer them from just observed words. It's rare to use a hidden Markov model in practice for either of those things, but it's a nice way to introduce hidden Markov models. But they are actually still used quite a lot. I think it's useful to know about them. But up until the 2010s, hidden Markov models formed the basis for basically all speech recognition systems. Since then, neural networks really took over and have been increasingly doing so. But I still think there's quite a lot of systems out there that uses a hybrid system between a hidden Markov model and a neural network. And that's because the hidden Markov model technology was so mature, so they basically merged the two. And they use, for instance, a hidden Markov model decoder or something, while getting your probabilities basically from a big neural network. So they're still actually used in practice. It's really good if you know about them.